Okay, we're live, we're rolling. Okay, so we're going to go back to example 4 from Friday, and we're going to use kind of an alternate strategy. The way we did example 4 was we realized we needed the derivative of height with respect to time, and if you just take the formula and just use it as is and derive it, do the derivative of it, you end up with the derivative of velocity with respect to time, the derivative of radius with respect to time, and the derivative of height with respect to time. Well, another approach to doing it is, instead of doing the derivative of the formula the way it is, what if we did the replacement of one variable for the other first? So let's try it that way. It actually probably is a little easier. So let's see. So here we are. Same example. Water is flowing into a conical tank at a rate of 5 meters per second squared. If the radius at the top of the cone is 2 meters, and oh, I forgot to grab my pen. Hold on. Okay, so the height is 7, and the depth of the water is 4 meters. Then how fast is the water level rising? Okay, so here's how we're going to do this. This time, I'm going to say, okay, so this is, I'll just call this alternate strategy. And it's not that much different a strategy, but I'll put it in words. Since we know we are solving for dr by dt, right? Oh, no, wait a minute. Sorry, that's not right. We're solving for dh by dt. That's better. We replace all terms, or terms, factors, whichever. In this case, it's factors because the formula only is a monomial, but this would be the strategy in any case. You replace all terms and factors containing an R with an equivalent, I just misspelled equivalent, expression in H. Then apply calculus. So the last time we did this, we just took the formula, did the calculus first, and then played with it. This time we'll do it the other way around. We'll play with the formula first, get it to a form we like, then we'll hit the calculus. Okay? So once again, I won't bother redrawing the diagrams. You should still have those. We could just look over at them, right? Right? The diagrams, because we know that the entire cone has a height of 7 and a radius of 2, and we know that anywhere you have the water level will create another triangle, in this case the yellow one, that's proportional to the big one, I can say that using similar triangles, the proportionality, the ratio of radius to height is 2 to 7. So that means that every time I see R, I could replace it with 2/7 H. Okay, we'll break for O Canada. All right, we're back. There. Okay, so we do, of course, also have our formula now. Our formula is the area of a cone is 1/3 times the, I should say the volume of a cone. The volume of a cone is 1/3 times the volume of the cylinder its base would make. And the volume of a cylinder is pi r squared h. So now, instead of just doing the derivative of this thing, I'm going to replace r with 2/7 h. All right. Then we'll simplify that a bit. We'll take everything that's a coefficient. 2/7 squared is 4/49. And then, of course, h squared times another h is h cubed. And then we'll do the derivative of that. Okay, so the derivative of v with respect to time. So we're doing the derivative with respect to time. So that creates a variable on v. 1/3 pi 4/49. All of this is coefficient. So of course you can just bring it out front. And then you're doing the derivative with respect to time of h cubed. So the derivative with respect to time of h cubed is chain rule. And you could also think of it as implicit differentiation because, again, we're differentiating not of the variable h, but of the variable t. So this ends up being 3h squared times dh by dt. All right, and at this point, go back to our givens. We want dh by dt, right? That's what we need to solve this for. But we know that we're looking for that change in rate when the height is 4. And we also know that unlike the height, which is changing at every instant, right? This rate is changing for every instant. This rate's constant, right? You're dumping the water in at a constant rate. So dV by dt is, for the entire problem, 5. So let's replace those variables. So that's a 5. That's 4/49, and then 3, and then h is 4, so 4 squared. And we're solving for dh dt. Okay, so let's tidy all that up. All right, let's see. That would be 4 times 4, or 4 squared is 16. 16 times 4 is 64. So that's 64 times 3. I think I'll just leave that as 64 times 3 for now. Times pi, all over 3 times 49. And the 3 times 49, so 3 times 49 times dh by dt. And the 3's cancel, which is nice. And then, okay, so I need to isolate for dh by dt. So I need to divide both sides of the equation by this fraction, which makes it a times the reciprocal. So I end up with 5 times the 49 on the top and the 64 pi on the bottom. And good enough. At this point, I'm going to punch buttons. So that ends up being the same thing I got last time, which is 1.22 meters per second. So there we go. So that's a different way to approach it. Now, you might be thinking, that seemed easier. Why wouldn't we always approach it that way? Well, kind of like, why do we need implicit differentiation in the first place? Instead of, remember the very first examples we did with the ellipse, where we just rearranged the equation so it was y equals, then you never have to worry about differentiating in two variables. Well, the formulas we're doing right now are actually pretty easy. Right? I mean, volume formula, come on, you could do that in grade 8 or 9. As you get further into calculus, you'll start working with formulas and having to do derivatives of equations where you couldn't easily represent one variable in terms of the other. Even something like, say for example, even in physics, right? Suppose, let's see, delta S is equal to V naught delta T plus 1/2 A delta T squared, right? Think about that formula, and what if all of a sudden you wanted the derivative with respect to time? Could you easily replace those two things with time? Could you quickly and easily rearrange that formula so that you replaced these two variables in terms of t? Probably not. So you're going to hit places where this strategy doesn't work. You have to go back to the first one. But just about all the ones we're going to give you are not complicated physics or geometry formulas. They're all fairly basic. Having said that, somebody did ask the other day, do we have to memorize and remember these geometry formulas? No, we'll give them to you. If you don't remember volumes and surface areas and stuff, don't panic. We'll give that to you. Okay? The only things we won't give you is, we won't give you the chain rule, we won't give you the product law, the quotient law. You got to know that. Okay? So, one more example. Example 5. This, I think there's about 4 or 5 on the worksheet that are like this one that I didn't assign yet. So after we do this example, you can do the whole worksheet now. All right, so how do we start this guy? A 6-foot tall person is walking away from a 14-foot tall lamppost at 3 feet per second. So I'm going to draw the situation here. Here's the lamppost. We're going to assume the lamppost makes a right angle with the ground. And here's the person. I might have exaggerated how much taller the lamppost is than the person. We'll assume he's making a right angle with the ground. And that creates a similar triangle situation. I'm going to put some variables on here. Obviously, that's not a variable. We know that's 14. This is not a variable. We know that's 6. But the distance this guy is from the pole, I'll call that x. That's definitely a variable, and it's changing. So I could even say in words, let x equal distance from pole to person. That means I need an actual expression for, or a variable for, how long this distance is from basically how long the shadow is. I'll just use S, and I'm handwriting S. So if you're wondering what the heck, that's not alpha. I don't like printing S because it looks too much like a 5. So I'm going to handwrite S. So I'm going to let S equal length of shadow. And then that's basically all I need for part A. How fast is the length of the person's shadow changing? So I'm looking for ds by dt. That's kind of what I would like to solve, right? What do I know? Let's organize my givens. I know dx by dt is a constant. The person is walking away at a constant rate from the lamppost. He's heading that way at 3 feet per second. Okay. So that means ds by dt should actually be kind of should be shrinking. Oh no, I guess it should be, no, it's probably getting, it's getting longer. Sorry, it'll be getting longer. And we want to find this when x is 10, right? And of course, x is changing at a certain rate, so that's going to be like an instantaneous change. And can you see the similar triangles? Do you see that this, here, let me split them up. The situation has 2 triangles, right? A 14 by s plus x, and a smaller version that's exactly the same shape, just a different size, right? They are proportional to each other, which means I can make a ratio of any 2 lengths, and they should be proportional to each other. So I can say that the base over the height for the little triangle has to be exactly equal to the base over the height of the big triangle, right? And that would always be true no matter where this person was standing. The 2 triangles that the situation makes have to be equal to each other by proportion. Remember, this is the basis for all trigonometry, right? What is sine? Well, it's height divided by hypotenuse. What's tangent? It's height divided by base, right? It's got to be proportional for any triangle that has the same angle in it. Okay, so from there, let's turn this into something like a formula. So this would be 14s equals 6 times s plus x. So I can say that 14s is equal to 6s plus 6x. And I'll collect my s's. 8s is equal to 6x. So s is equal to 6/8 of x, or simplify that, 3/4 of x. So there we go. We can now replace the s with, or actually, we can actually just use this as an equation. S is equal to 3/4 x, right? We know what x is, or we know that at one point, we know a point where we're solving for x. We're solving for x when it's 10. So let's just do the derivative of both sides of this equation. Derivative of s with respect to t is equal to 3/4 times the derivative of x with respect to t. And that's going to be 3/4 times, we know dx by dt is 3, so I should keep that there. And so the final answer is 9/4. Might as well take that to a decimal. 2.25 feet per second. So the shadow is growing at a rate of 2.25 feet per second. And kind of like that ladder problem, if you weren't kind of understanding how this situation is behaving, you might automatically think the answer to the B question is the same as the A. Right? It's like, well, wait a minute. If I know that this shadow, right, this length here is growing at a rate of 2.25 feet per second, isn't this entire length growing at that rate? And the answer is no, because this x is growing at a different rate. So if I am asking you in the B question, how fast is the tip of the shadow moving away from the lamppost? That's not quite the same question as how long is the shadow, or how fast is the length of the shadow changing. So I'm going to redraw my triangle. I mean, it's the same triangle. The lamppost is 14. The guy is 6. But this time, I'm going to just maybe call this entire length here Z. So I'll say let Z equal distance from post to shadow tip. Right? If you're wondering, well, why don't you just stick with the same variable as you had? Because I don't need a variable for how long the shadow is, and I don't need a variable for how big the distance is between the guy and the post. So why use variables you don't need? Okay. Oh, actually, I guess I still do need the shadow, because I do have to compare the triangles. So there, it's the x I don't need. Okay, and what I'm looking for is dz by dt, right? How fast is this point here moving away from that point? So at what rate is this distance changing? And once again, I'm going to set up similar triangles, right? I have a triangle that's 14 by z, and I have an exactly the same shaped triangle that's 6 by s. So 6 over s is equal to 14 over z. And let's make a formula out of that. 6z is equal to 14s. So divide both sides of the equation by 2. 3z is equal to 7s. I'll do this one a little differently. I'll leave that as my formula, and I'll do the derivative of both sides now. So the derivative with respect to z is 3 dz by dt, and the derivative with respect to s is 7 ds by dt. And we solved for what ds by dt is in the last example, in the last question, right? It was 2.25. I'll go back to fractions. It was 9 over 4. So my dz by dt is going to be 7 times 9/4, and I'm dividing both sides of the equation by 3, so I could just put it there. So that makes that a 3. And I get 21 quarters, might as well make that a decimal again, 5.25 feet per second. Did I say on the last one it was feet per second, or did I say meters per second now? No, I did say feet per second. Okay, phew. Don't lose a half a mark for using the wrong unit. And there we go. That's the last type. There's a bunch like this where you have two triangles that are similar, but one of their parts is moving. And of course, if the two triangles share that part, they might be moving at different rates from one another, and that's where the calculus comes in. Right? That's another way you can think of calculus in general, right? It is the mathematics of solving for variables that are changing on you. So that's a pretty good way to define calculus. If somebody's asking you, what are you doing at school? Well, I'm doing calculus. What's calculus? It's like, well, can you picture algebra? Imagine algebra if the letters that you're, the unknown numbers you're solving for are changing on you while you're trying to solve them. That's essentially what calculus is. Okay, so cool. I'm going to stop the video. Lesson's over. And let's have a